Now let's have a look at a finite element program, a small program prepared for the analysis of a static problem of a beam. This program will not include the numerical integration, just it's there to demonstrate how we can create and solve a finite element problem for a beam. The following video will use the same program but with a numerical integration method. Here, as usual, I started with clearing all, then clearing the console. That's to remove everything written on the FreeMat console. Now, first step, I defined the number of elements to be 5, the length of the beam to be 1 meter, width of 2 centimeters, and thickness of 1 millimeter. The modulus of elasticity is 71 gigapascal. Sorry, this should be a 9. 71 gigapascal, which is the aluminum stiffness. And I also added here the density and the thermal expansion coefficient. They are not going to be used for this program, but may be used for further programs. The first step of calculation is getting the cross-section area, which is of course the width times the thickness. Then the second moment of area, which is bh cubed over 12. Here it's the width times the thickness cubed divided by 12. And then the length of the element, which is the total length over the number of elements. Here you can see this is the stiffness matrix of a beam element. I call it K element. It's the modulus of elasticity times the moment of inertia, the second moment of area. Of course, this assumes that the moment of the second moment of area and the modulus of elasticity, EI, which we called the flexural stiffness, is constant over the beam. Then here you get the 4x4 matrix. Each row represents one of the rows of the matrix. Then at the end, I divided the whole matrix by the cubic, by the length cubed, the length of the element cubed. Okay, this is what we got from the integration using Mathematica. So let's see what we can do to assemble the elements that create the global stiffness matrix for the beam. First, remember that each node in a beam has two unknowns or two degrees of freedom. These are the deflection, the displacement, and the slope. So since we have n plus 1 nodes, the size of the global stiffness matrix should be twice n plus 1 times twice n plus 1. It's a square matrix, of course. So this is initiating the global stiffness matrix by filling it with zeros. The following step is assembling the elements. Now remember that we used to put each element, each stiffness matrix on the diagonal of the global stiffness matrix. So we get here this relation. Let's just focus on this part of the submatrix. Here it says that for the ith element, take the 4 rows corresponding to the ith element. If you substitute I by 1 here, you'll get 2. 1 times 2 is 2 minus 1. So the first row is the first row, and the last row is 1 plus 2, 1 plus 1 equals 2 times 2 is 4. So this actually takes the first 4 rows of the matrix, and this also takes the first 4 columns. So here you can see the same indices are used 2 times I minus 1 to twice I plus 1. This is where we're going to put the first stiffness matrix, element stiffness matrix. And as you can see, just like what we did in the bar, you are just getting what's there in the matrix and adding to it the element stiffness matrix, then putting it back in its same place. Just to check, put n equals 2. You'll find that this starts from the third row here, third row and third column. Then this will be the sixth row and the sixth column, and so on until you go through the whole all the elements and assemble them. Each of them, they all have the same stiffness matrix. Remember, in this very special case where we selected the element lengths to be all equal. So by the end of this loop, you have populated the global stiffness matrix by adding up all the element stiffness matrices on the diagonal and getting the global stiffness matrix. After we populated the global stiffness matrix, now we need to apply the boundary conditions. In this case, we are saying that the boundary condition that the beam is a cantilever beam, meaning that it's fixed from one side and free from the other side. So what we have here is we are going to eliminate the first two rows and the first two columns of the global stiffness matrix to get the reduced stiffness matrix, which is the one after applying the boundary conditions. Further, we're going to create a force matrix, a force vector, which is initially all zeros. Then we'll just multiply, add a 1 there. Here the 3 times EI is just a number that we're going to use so that the output will be always 1. The maximum deflection will be 1. Anyway, finally we get the displacements by inverting the global stiffness matrix and multiplying it by the force. Let's see here that when we run this program, here you are. What we got is the displacements, and as you can see, the first two rows and two columns are zeros. The first two W's are zeros. Then you get here the displacement, slope, displacement, slope, displacement, slope, displacement, slope, and here you are. This is the last displacement of the beam, which gives you a 1.0. This is to check that the program is running properly. You can revise this from mechanics of material. The deflection of a beam is going to be a 1. So this program runs properly, and it demonstrates how we can create the global stiffness matrix for a beam with elements that have the same length and have a constant modulus of elasticity and second moment of area. Next, we're going to illustrate. We're going to use the same program, but while calculating the stiffness matrix using a numerical integration, just for the purpose of illustration. As you can see, we can get it in closed form, but to illustrate how we perform the numerical integration and get the same results. A copy of this program will be linked below the video and course website, And if you're watching this on YouTube, just follow the link below the video to guide you to the course website.